Okay. Oops, my camera's not aligned. Okay. So last time on simulating a quantum computer, we got to an exciting moment, I think, where we were able to come up with or start to stub out the order finding algorithm, which is the main component of Shor's algorithm for simulating a quantum computer. But we ran into some performance bottlenecks, and this was somewhat anticipated. And so today we're gonna get to do something that I really enjoy. I just find this aesthetically pleasing when this happens, where you've implemented, excuse me, where you've implemented something and not optimized it, but you kind of know in the back of your mind that there's a better or another way to do it, one that you want to implement now that's going to have most of the same behavior. Maybe it's a slight superset of the behavior, maybe it's completely the same, but it's going to be optimized, and you get to do that in an environment where you already have your unit tests in place. So we have how many unit tests? Like 50 plus unit tests, I think. I'll run them now and find out. And this one's gonna. Is this one gonna bomb? Oh, I have a couple that are slow, but that's fine. I think we have like 50 some odd tests. This one's gonna bomb out though. Let's comment this one out for now. This is the one that's gonna pass once we do our optimization. So we have all of these tests already, and it's going to enable us to really effectively and efficiently refactor into the state that we want to refactor into, which is super cool, and I think always seems super satisfying from my perspective. It sort of vindicates and justifies all of this time that we spent writing tests. So excited about that. The main problem, if you weren't around last time or don't remember, the issue, and I want to get rid of this test identity gate also, which I think I just jumped there. No. Gate test identity gate. We put a 10 qubit gate in here, which is good for perf testing, but it is pretty slow. There's a way in Rust to set up benchmark tests. I have done it before. It's quite slick. I just don't really want to do it at the moment because we're not really benchmarking. Like, I know why it's slow. I don't need to benchmark it. Is this still really slow? Test identity square matrix. Yeah, same story. This one, I'm just going to 5. Okay. These were the tests that we were using last time in order to figure out where the slowness was coming from. Is there one more that's slow? I don't know, we can see when it finishes running. Well, we can see when we run it later. Okay, so if you don't remember where we got to, the point was that we're simulating a quantum computer, and for a 4-bit qubit system, even 5, I think we were okay. This is a little bit jittery, but it's not super slow. and some of that's the visualization. The issue we start getting into is that these colored things are representing matrices of complex numbers, and the size of that matrix is 2 to the number of qubits squared, right? There's 2 to the, so there's 4 here, so there's 2 to the 4, 16 here, and there's 16 columns as well. And that number grows exponentially, and it basically, we were getting bottlenecked on needing to perform matrix multiplication. So we're using a super fast library for it. It's a Rust, linear algebra library, should be really fast. But the problem is, if we, in Shor's algorithm, even for a really small, like a really trivial run of it, we still need 12 qubits, and that's going to be 2 to the 12 by 2 to the 12, and doing the matrix multiplication on each of these was just prohibitively slow at that scale. And so what that means is essentially we realize that there are a lot of zeros in all of these matrices. They're really sparse. And there are algorithms for multiplying sparse matrices, but it feels like what we've done is kind of aggressive, right? We've taken something that looks like a circuit diagram, something where really this gate only needs to feels like it should only need to get applied to 2 qubits, but here it's getting applied to 16. These only seem like they need to get applied to 2 qubits, and they're getting applied to 16, and so on. And so what we want to do is implement a new version of quantum circuit that is a little bit more like a circuit diagram. That's a little bit more like which qubits get mapped into which gates. And then if we want to, we can always turn that representation into this representation, and that shouldn't be too slow. But it won't be implemented that way. So we're going to start working towards that. And I'm just thinking, while I'm staring at this, I'm thinking about these different gates, and one interesting item here is the permutation gate, the gate that permutes all of the different qubits at the beginning, because this actually is or at least in general, it is a 16 by 16 matrix. It's a 2 to the number of qubits by 2 to the number of qubits matrix. So that one might be an interesting case. I mean, it should also be really easy to do matrix multiplication with a matrix like this. So anyway, that's probably a special case that we'll have to think about. But for now, let's, we should commit this. I went ahead and merged branch. Let's see here. Tests master. And we'll just YOLO this to main. I'm also trying out a new terminal. Today I heard about on Reddit, somebody posted about Michele and U-Shell, which is a Rust-backed terminal, and it's pretty cool. It thinks about. I've always found Bash to be a little bit. I mean, it's super cool and super powerful, but something feels not quite right about it to me. And New Shell has this really nice sort of paradigm where everything gets turned into tables. So you can see, even if I just ls, I just list the files in my directory, I get this table of data back, which you can then transform in cool ways. Like I could say ls and then get me the third row, and it gets me this row, cargo.toml, and so on. And you can do all sorts of interesting things from that. I'm not sure. I don't use the terminal that aggressively while I code. I really just use it for Git and manipulating walking around the file system, so I'm not sure how much it matters, but in case it looks different, that's why. Okay, let's check out a new branch, and let's call it circuit refactor. Okay. And let's think about what we want to do here. So right now our circuit very aggressively uses a list of gates. And so what we want to have instead is basically like a tree of gates. Yes, a tree. No, because it can have cycles. We want to have a series of levels of gates that can have different inputs and outputs. And we also still might want to be able to have this quantum circuit. Like a quantum circuit with this internal state might be useful. Although we could always just implement that within the new model of quantum circuits. Okay, so let's change this in place. I was trying to work out whether I wanted to like keep this struct somehow and create a new one, but I don't think I do. So what do we want the new model of this to be? Well, when we add a gate, we still want to do this. We still want this to be the API, where we tell it where we're adding the gate and what the input qubits are. So we're really only changing the internal model. And I guess the goal will be then to have a new function like right now we have get gates. We need a new function that's like get wide gates or something that blows all the gates up to get us back to the current setup. So let's see here. So I basically expect all of these tests to do the same thing as they currently do. And just the internals to change, and then we'll give it one more way of getting the gates. So how to change the internals. So basically we want to be able to say at each level of the circuit, so at each element of the vector, instead of just having one quantum gate that spans all of the input qubits, we want to be able to say, here's a layer of quantum gates and how they read from the previous ones. I wonder if we have a new struct that's like quantum gate layer, and that thing knows how to turn itself into a matrix. And it has from each of the inputs or from each of the outputs of the previous gate, previous layer, it pulls in the inputs. And then to compute the layer, rather than when we run, rather than just applying all the gates, we instead go through each of the layers, and the layer knows how to apply. I think I like that. Okay, let's start there and write some tests. Do I want this in a different file? I think I might. Right now I have both quantum register and quantum circuit in this file, which I don't actually love. So let's go quantum register .rs. Here we will say mod quantum register, and in quantum gate we are going to grab everything about quantum register. It's actually most of the file, and put it in here. And then we also will need all of the tests. Go away. And test, register. It's all about registers, quantum gate. Are there any others that are about quantum registers? Is this one kind of about? No, this is about gates. Okay. And then in here we're gonna have to import a bunch of stuff. Let's not do it from the tests, because then it only imports them into the tests. So import some things, import more things. What else we got here? Norm. Measurement, we probably, ooh, interesting. Where's measurement defined? Qubit, that's fine. And this should be brand. And what's going on here? This is too long. Can we... This is the one problem with it expanding out the type like this, is it kind of makes your... lines a little long sometimes. No complex exponent. I don't believe you. Oh, we need complex field, which doesn't auto import for some reason. Okay. And then iter, sure, we can just pull that in from here. 0 though. I actually do want to, well, I don't know, maybe I don't. Because if I don't use it, I don't want to import it. And tau. register needs some fixes also, or quantum gate does rather. So now there's some stuff that's not being used at all, which doesn't surprise me. And we need quantum register. And we do need qubit. Why was, oh, because it's, okay. Quantum register. Vector 2. Why am I doing anything with vector 2s here? New normalized takes a vector 2. Oh, interesting. I did not remember that. Okay. Sure, this can just be in the test. And now everything in here is passing. This be fixed. And same story here. And same story here. Okay. And cargo test, and we'll also see how long these tests take. Whoop. Could not compile. We need to cargo clean. Yeah, sometimes if you haven't been in the repo for a few days, especially if you're on the nightly version, you can have weird stuff where you need to cargo clean before you can compile again. Pull in all the dependencies again. Okay. That's going to take a little time. Okay. Let's actually get all get commit factor quantum register out of quantum gate origin. Where am I? Get get push origin circuit refactor. Okay. Cool. And next up, now we're gonna have a new one called quantum gate layer. And maybe quantum gate layer. I mean, I'm maybe making the exact same mistake again, but maybe we put it in here. It shouldn't really be getting used outside of the quantum gate itself. So let us work out what we want the API for quantum layer to look like. Quantum gate layer, quantum circuit layer. Actually, let's put it in quantum circuit. Now that I think about it, it is a circuit layer, not a gate layer. Okay. Quantum circuit layer. What instantiates as gate. Seems like an okay starting point. Let layer equal quantum circuit layer new . and GitHub is giving us a bad suggestion. So we want the circuit layer to have multiple gates, and each of the gates can... So first of all, we're going to need to know how many qubits it is. Second of all, we're going to be able to have multiple gates, each of which has different inputs. So probably the simplest simplest way of representing this is a list of gates and then a list of input gates where we work out within the type, like on construction, which gates have which inputs. But that's awful ergonomically. So like something like something like this. Back 0, 1, 2, 3. Which doesn't seem too bad, right? It's a Hadamard gate applied to the first Hadamard gate goes to the first input, and so are the first previous output, and so on. The trouble is, like, suppose this is a C0 gate. Now you need this. You have something like this. Now it's like the Hadamard is the 0, but the C0 gate, which is a 2 input gate, is 1 and 2, and then Hadamard is 3. And it's like, yes, I can figure out which ones go to which ones, but it's ugly. An alternative is something like this. Which I like better. It's nice and explicit. We can give this a type also that's descriptive. Yeah, I guess that's what I want. I guess that's what I want. And then we will do assert layer as gate is equal to quantum gate new or I guess it's just quantum gate Hadamard dot tensor product C0 dot tensor product Hadamard. Right, that's how that should work. Our tests over Phillips. Quantum gates compose. because this doesn't work yet. Okay. Hopefully that makes our test faster though. Okay, so what to do here? Quantum gate Hadamard, blah blah blah. I'm not. It's that I need almost equals, and then this whole thing is parend. And there we go. Tensor product takes values. Tensor product takes values. Okay. And I'm actually gonna do it. Whoops. This way. Just because I think it's going to make it more legible. Whoops, and we're going to want 0, 1, and 2 here. Okay, and then we can do more complex ones in a bit, but I want to start with a simple case. Okay, so let's get to implementing this. Okay, struct, and I don't think it has to be public, but we'll see. Qubit layer. And quantum gate with inputs, we're gonna say. And this is gonna be a private type alias where we say type quantum gates with inputs is that. And then let's go back to our quantum circuit layer and import this. And we should give this some derives. Clone is a good starting point. And I guess we should also, so before we import quantum circuit layer, we should also import debug. Let's see here, display and debug. Display for quantum circuit layer. I mean, we're going to want to do something a lot nicer than this, but I think it's okay for now. And impl debug for quantum circuit layer. And for this, I think we can just write self dot. Can we just say self dot debug? Let's see here. Write f to return. No, just self. Did I not already have to import debug here? I did not. And how do we usually do this? Debug, we return a standard format result. Okay. And push spring. Okay. Sure. For now, let's just do debug because that should work. Okay. And this still doesn't work because there's no new function yet. Okay, so then pub function, sure. The thing's not pub function new. I'm pretty sure I just always want to provide the vec gates vec quantum gate with inputs, and this is just gates. Okay, and now pub function as gate. And here, this is wrong. Here we will need to do what we've already done in the old implementation of the quantum circuit, where we added the gates. So in our previous implementation of adding the gates, we are always, it's interesting. We're always just we're always adding one gate at a time. So a naive implementation here would be to do the same thing and then matrix multiply, which I think I like for the time being. So let's steal this function because we're gonna be writing rewriting that function later, but I want to use it here. So as so there's going to be a function. Is it going to be add gate? No. It's going to be a private function. It's not going to take self, and it's going to be get broad gate, we'll say, and then so we have self in here, which we won't want. We'll just instead say return gate to add, and let's call this broad gate. And then we also need n qubits, u size. And all the self.n qubits become just n qubits. Okay. And so now for add gate, as gate, we say for gate inputs, input qubits in self.gates. See here. Let mute broad gates be new vector, and then we say, I mean, this is a really naive implementation of this because it's going to do a bunch of matrix multiplication, which we actually don't want, but it's good to do this in small steps. So then what do? We say broad gates dot push self get broad gate n qubits gate input qubits self dot n qubits, and then this needs to return a quantum gate, and then we can just collapse these by going through them, and we can return gate. Can't move out of self gates. Sure. We can clone these. Well, actually, we shouldn't need to clone them because we shouldn't need this to be anything other than a reference. But gate is going to have to be cloned. Okay, let's test our, so let's cargo test in the background here, just because I want to see how long that takes at the moment. And then let's test our quantum circuit as gate, and it fails. It fails because they're not almost equal to one another. Are we doing or composing in the right order? For broad gate? No, we're not. We need to compose in the other order. Yeah, we need to compose in the other order. Still didn't run. Still says they're different. Okay, let's do a trivial case first. Circuit new 2, add gate. Let's just make a new 1. And we'll just add gate at the beginning. And then assert layer as gate is almost equal to a Hadamard gate. Oh wait, what? As gate returns quantum gate. Quantum key. This is not how new works. GitHub doing a bad job. Okay, add gate. This just becomes vec. This, and we need a semicolon. And this needs an ampersand. Oops. This needs circuit layer. There we go. It's a little more like it. Still failing. Failing at... Yeah, okay, so this one's passing fine. Okay, my test finished very quickly, but it hit the failure case, so that actually doesn't prove anything. Okay, let's do the C0 case. 2, 0, 1, and C0. Okay, same story. Okay. So as gate, for each gate, we get the broad gate for those input qubits. We should be doing some validation up here, by the way. So, namely, let input qubits be input qubits. We flatten them and collect them. No, I need them to be distinct. So vec this, and then let's gate that one. And then let's make sure they're distinct. This is a thing. How about, let's see here. I mean, one way to do it is to stick it in a hash set, but okay. So unique is a thing, but it needs to be brought in from itertools. I've used itertools before. Okay. And the thing is still thinking. Build also going to want to we also want everything to be less than the number of qubits. I don't need them to be equal though, so let's assert that the max is less than n qubits. Okay, but that doesn't help with the problem. The particular problem we had, which is still that our results aren't equal to one another. Okay, let's continue doing specific tests. So these are fine. But now what if we do quantum gate Hadamard? 0 and Hadamard 1. Just continuing to drill into where it's easy. It's usually better and faster, I find, to write more tests to debug rather than like going into the debugger or staring at the implementation. This needs to be almost equal to Hadamard tensor product quantum gate Hadamard. Doesn't need to be referenced. Okay, so that worked actually, which is interesting. It's kind of expecting that one to fail. Is my order right here? Yeah, because tensor product is associative. And I trust my tensor product. 0, 1, 2, 3, 4. So a C naught with 1 Hadamard. Or what's a better way? I can just do a knot with 1 Hadamard. Just trying to hone in on the error. Okay, so this fails. Kind of makes it feel like an order thing. Let's look at what this returns. So not applied to the 0 gate, and then a Hadamard applied to the 1 qubit. So what should that do? That should take the... Oh, you know what we can do to simplify this? So that's another good test, is if we do not and identity here. 1 or 2, no, 1. Okay, so not and identity. Ends up looking like this. And so a not an identity means identity is getting applied to the first qubit. So what we would expect is that 0, 0 goes to 0, 1. 0, 1 goes to 0, 0. 1, 0 goes to 1, 1. And 1, we would expect it to be like this. So 0, 0 is the basis corresponding to this, so it goes to 0, 1, that's correct. 0, 1 is the basis corresponding to this, goes to 0, 0, that's correct. 1, 0, 1, 1 corresponds to this, but this looks right. My tensor product is wrong. Somehow my tensor product is backwards from what I think it should be. Is it this? And now we get a different failure. Yep, that's what it is. Interesting. I wonder... I wonder if I believe that this is the right order. Hadamard, C naught. I guess I do, because then I read left to right. Like, this is the farthest right basis vector, or the far, like 0, 1, 2. We're going right to left in some sense. I think this makes sense. Okay. Okay, so that works. Let's commit that. Quantum circuit layer as gate. Okay. And let's see how long our tests are taking to run. Not very long. Why? What failed? Square matrix identity. I did something to this. What was it? 2 to the 5. 2 to the 5. What's wrong with this? Failed. The assertion failed. Matrix. Identity, 2 to the 5. Matrix size is 2 to the 5. New normalize. 2 to the 5. 1. new normalize, and I multiply them together. Dot norm minus v dot clone dot norm is less than a very small number. Okay, that did it. Test. Okay, everything passes and it runs quickly. Great. Cargo add. Make test deterministic. Yeah, why? Oh. Git add all. Git commit. Git push. Okay. Okay. So that's a start. Next. Let's put another test in here, which is the inverse of this test, or like somehow slightly more complicated. Like if I flip a C not gate, what's the right test here? That's not too much of a pain. Rather than doing that one, let's take this one. And let's make it a 3-qubit system. Let's make it a C naught of 2 and 0 and a naught of 1. So then 0, 0, 0 goes to 0, 1, 0. 0, 0, 1 goes to 1, 1, 1. 0, 1, 0 goes to 0, 0, 0. 1, 0, 1 goes to 1, 0, 1. 1, 0, 0 goes to, certainly the one in the middle is right. Yep, that's right. 1, 0, 1, that looks wrong. This should be 1, 1, 1, yeah? Oh no, that's right. 1, 1, 0, good. Good. Is that all 8? That's all 8. Okay. So then I'm not going to be able to construct these with a tensor product. Instead, I will just... Actually, can I construct these from a tensor product? No. We'll just say... assert layer dot, let's see here, let gate be layer as gate, assert gate dot apply quantum register basis 3, 0 almost equals 3, 2. 3-1, 3-7, 3-2, 3-0, 3-3, 3-5, 4-6, 5-3, 6-4. Yep. And 7-1. All right. Cool. Okay, so that's pretty convincing. Okay, so now we get to start messing with the internals of quantum circuit. So quantum circuit will now be a vector of layers. And I guess I'm going to go ahead and call this layers. It will be a vector of quantum circuit layer. We can keep that as it is. And obviously this breaks stuff. Okay, so add gate should no longer do this. It should instead update the layer. And the way that it should do that is by saying so certainly we should be able to add layers. Add layer, add meet self, layer, we post the layer on. First we assert that the layers have the same length. Interestingly, our circuit and our layer are now a little duplicative in terms of they both carry around information about how many qubits they have. I think it's okay. So if we want to add a single gate, for now, let's just say it creates a whole new layer. Hang on, new quantum layer. Let's make this. Let's just have a from gates. And qubits gate. And then self.add layer. And this will be self.add qubits. Okay, and then from layer, front gate and qubits. Gate, quantum gate. And no. This is just this goes away, this goes away. And oh, I guess we need to know, right, input qubits. Input qubits. Okay, a little convenience function. And this still needs input qubits. Sure, it's fine either way. Okay. So now if we add a bunch of different gates in, they're all going to be on their own layers, which is a little bit kludgy, but we can sort that out. And now when we run, we instead want to, let's call this layer, and layer.apply. Yeah, that's a thing that a layer should be able to do. Let's call this get layers. And this will now return a, ooh, I guess we don't want to do that. All right, we'll work out what we want to do there. And then add gate will be for layer in self.layers. Let broad gate be layer as gate, or I guess we can just say layer as gate. Okay. Okay, so we need layers to be able to apply themselves. That's something we should write a test for. Test quantum circuit layer applies. Layer B quantum circuit new Hadamard 1. Sure, that's fine. And then layer apply quantum basis. Typically say not because it's easier. Quantum basis 0 maps to 0. And 1, or sorry, 0 maps to 1, and 1 maps to 0. And then a slightly more complicated case would be what? Sure, we can do a C naught, but let's do it inverted. And then so an inverted C naught means that 0 gets mapped to 0. 1, though, gets mapped to 3. 2 gets mapped to 2. and 3 gets mapped to 1. And now let's apply. And this will take a self and a register. It will it needs to grab just the basis vectors that it needs. Is this kind of this is I don't want to look at this. This is what GitHub is suggesting, which I don't think is right. Yeah, so it needs to go for gate input qubits in self gates. I don't want to do a huge matrix multiplication. So instead, I need to pull the vector apart. So I need to say so I don't want to just multiply. I want to just pull the register's vector apart. Let me to return be sure. And then I want to do this without multiplying by a matrix. These are guaranteed to be unitary. But they do get applied at a qubit by qubit basis. So how does this not end up being... How does this not end up being a big matrix multiplication? That's what we need. If it's a big matrix multiplication, then we get into trouble. We get into perf trouble, which is what we've seen before. But the matrix multiplication is basically saying, listen, here's how you transform each basis vector. So here it is. But that's essentially the same thing we're trying to do here. We're trying to... We know which qubits are being applied, are being transformed, and therefore we can work out which basis vectors need to be transformed and how. But the way you do that is with a tensor product and matrix multiplication. So we've come back full circle. Maybe have not solved our problem. Because, like, for instance, let's say that we have, I mean, our test example, right, it's a C0 gate. Let's say that we're doing this over a 5-qubit system or something, though, and we're applying it to the last two. That still changes every basis element. We still have to specify how every basis element transforms. Okay. Well, if that's the case, then maybe we can't optimize it the way I thought we could. I wonder how sparse matrix multiplications work. Okay, so the point is going to be that a whole lot of the matrices are a whole lot of the elements are guaranteed to be 0. see here, Rust, sparse matrix. And algebra sparse, look at that. Okay. So this might be better. This might be better. Okay, let's see. And this happens sometimes, right? You have an idea about how things are going to work out. And then, I mean, ideally you realize it. If it's not going to work, you realize it ahead of time. But this hasn't been too bad. Let's take a look at our commit history, because I want to revert, but I don't want to revert all the way, I don't think. Yeah, so like I want to take these two commits, but not this commit. Quantum circuit layer is gate. But okay, so I can revert this, and then alright, so what we'll do is we'll stash this as a separate branch. So git stash, git checkout be attempted circuit refactor, git stash pop, and then git add all, git commit m, stash the failed attempt, git push origin, and what did I call this? Literally 12 seconds ago, attempted circuit refactor. Okay, and now git checkout, circuit, nope, what do I call it? Refactor, nope, git checkout. Circuit refactor. Okay. And so now nothing should be failing, everything should be working, cargo test, and then we'll just get rid of the circuit layer. Yeah, because we haven't actually incorporated it at all. So these tests go away. And circuit layer. And these go away. Okay. Sort of sad, but it happens. Remove quantum circuit layer. And then we'll go ahead and are we gonna merge this? No. we're not going to merge this. We're going to use sparse matrices. Okay. Carpet build. And let's work out what we need to do here. So I want to do algebraic operations. So I assume I'm either going to use CSR or CSC. Ooh, wait, that was a cool thing. What did it just say? Many iterative solvers only require matrix vector products. Do I only require matrix vector products? I don't know, we can just test them out. And these are okay. Let's see. Okay, so this built. And the nice thing is we should just be able to swap out the internals of the matrix. So let's just go CSR. So let's say that we have CSR matrix of complex. And let's get rid of our formatting, because I really just want to see how fast this is. Ugh, it doesn't implement normed. Okay, well, let's see how we do with this. New CSR matrix. Is square isn't a function. Determinant isn't a function. This is yikes. Okay, there's a lot of stuff missing from here that I would want. So probably not gonna do that. There are a couple others. And algebra has sparse matrix support. Interesting. So, I mean, what's going to be the point of these algorithms? The point of them is going to be that I don't have to do a bunch of the multiplications because I know where there are zeros. So if I look at a given element of the resulting matrix, it's a linear combination of things from the rows and columns of the previous matrix. And as long as those rows and columns don't overlap in some sense, it's always going to multiply out to 0. So if we fill, the algorithm would be some, why am I still saying CSR matrix here? Okay. So the point is going to be that if I can just allocate all my zeros and then compute only the terms that are non-zero, it's going to be faster. But to do that, I kind of have to be able to look them up quickly, and I have a feeling that the matrices themselves can't be looked up quickly. That's the whole point of having a different internal format. All right, well, I'm going to have a bit of a think about that, I think. And see whether I think that it's plausible that we could implement our own sparse matrix multiplication. It really should be, right? Like, I'm just thinking about thinking about these visualizations, which will show up in a moment. Right, these are really sparse matrices, and they get sparser as they get bigger. Right, the fraction of entries that are 0 gets bigger and bigger. So if I'm at some coordinate, like, this one, then the only way this coordinate is ever getting actually filled is if either its parent row, like the left-hand row or the right-hand column, have overlapping values. Which seems like I should be able to check pretty quickly. Especially if they're structured the right way. Right, like right now the bottleneck is matrix multiplication. When I, trying to remember. Trying to remember exactly where the bottleneck ended up being. I think it was in these, right? Yeah, like here I'm composing giant matrices together. But if I knew where the values were, then it could potentially be a lot faster. Like all of my matrices have something like, at worst, it's like they have 4 values in a 2x2 matrix, and then they get identitied over all the rest of them. So that's like 4 into however big the matrix is, sort of. This is interesting. So one approach would be to indeed replace the D matrices here with some sort of sparse format. Which seems doable. And then I wonder what it means by algebraic operations. Yeah, okay, this is kind of what I would expect. So maybe just during matrix multiplication I should try doing this. That'd be interesting. So what if we keep it as a square matrix for now, but then during multiplication we say, I mean, I imagine this is just going to change where the bottleneck is, but CSR matrix from, will this work? Seems like it can go from a normal matrix, but then it needs to get converted back. There's no way this works, is there? Let's see. I mean, this is obviously going to be terrible, but let's... But in principle, we could do... let's see here, let's just undo all of this for a moment. And we can say, let sparse... let self-sparse be push matrix CO matrix new self dot size self dot size should be mutable, and self sparse should be push matrix self matrix. What is the 0, 0 here? Where it starts from. Okay. And then let self CSR. Well, let's start with this and see what happens. Kaye. And then let result be, I mean, this is obviously going to be slow. And then results 2 dense. And these don't even want to multiply. They have to be references. Oops. Still don't want to multiply. Because you can't multiply in this format, you have to get CSRs from them. Let self CSR be CSR matrix from self sparse, and went only like this. Self CSR, right hand side CSR. Okay, and then 2 dense is not a thing. Instead, what do we do? Dmatrix from function. Let's see here. Dmatrix from function. Self.size, self.size. And then ij goes to wait, what? Why is it INJ? How do I get a dense matrix back? Matrix from result is what I want. That's not a thing. How do I get the dense matrix back? Get a D matrix back. Can't use into, right? That doesn't do anything. because it still doesn't have from defined on it, right? Format. Surely there's a nice way to get a D matrix out now. To D matrix and algebra. Yeah, this is gonna come up with anything. Convert. Ooh. Okay, but then there's no way to get back. What if I want to get back? Wonder if I ever need to get back. I mean, I really don't. Okay, so I'm running out of time. But my thought is that maybe we go ahead with trying it with CSR. And we can leave it, we can give it some D matrix, like we can just have that be the internal representation. We can leave D matrix as the external representation. It's just like a little kludgy that it doesn't allow us to convert back into a D matrix. But I think we can work with that. And then in principle, these algorithms should be a lot faster. Matrix algorithm speed. Okay, I'll need to look into this, but I think this might be the path forward. So I'll be back tomorrow with some answers here, and then we'll go forward from there. Cool. Hope everybody's having a good day. Happy Monday, and see you tomorrow. Take care.